Good morning, Year 12. Thanks, guys, for coming along. I know it's early, 8:30 in the morning. I bet some of you guys are like, oh, but you're still in pajamas. That's ridiculous. Anyway, so today we're going to be looking at, just need to make sure that I pause my other thing. Yeah, okay, cool. Right, so today we're going to be finishing off alcohols. At least that's the attempt it's going to be to finish them off. We've got still quite a lot to do, really. It's all a little detailed stuff. We should be able to get it done. I'm very aware that we're still missing a few people. We're still missing Ria, we're still missing Jasmine, still missing Ben, still missing Ivan. Just thought I'd give them one more minute, see whether or not they decide to show up. If someone could give them a message, that'd be ideal. I'd really appreciate that, guys, if you can. Otherwise, I'm going to crack on. Right, let's share my screen. There we go. And then I'm actually gonna turn off my camera since I don't need it. Disable device. It gives me, it just gives me a little bit more time before my screen decides to go shaky. Okay, so alcohol part 2, Nikita. Oh, Jasmine's here. Hi, Mr. Duncan. Our exams are cancelled. What happens? Yeah, Nikita, that's a really good question. Okay, so number one is they have been cancelled, but there is a chance that they could end up coming back online if everything calms down. Obviously, that isn't guaranteed. There is a chance that they may stay cancelled, but for you guys are actually in the unlucky situation of it doesn't matter because you're just going to do your A2 exams next year, and you'll probably have to do the ASs as well, which will be a nightmare. You might have to do all of them, perhaps. I don't know, Nikita. It's going to become complicated, but don't worry. We will get it resolved. It will be fine. It's much more problematic for actually the year 11s and the year 13s who won't have a chance to do theirs again. But as I said, we're sorting it. Okay, so last lesson, we were doing alcohols and we were doing the oxidation of alcohols. I wish we could have been doing the practical, but we couldn't be. So I talked you through it. I said for you guys to have a look on the booklet. I will post some questions online. I've managed to go and lose my pen. Where's my pen gone? There it is. Okay, so is anyone else there? Oh, Ivan's just arrived. Winner. Right, I'll just finish off the register. So we've got Jasmine, we've got Ivan, yay, Ivan. Cool, Ivan's here. Still missing a couple, but we're nearly there. Right, so last lesson, we were talking about the oxidation of alcohols, and we drew reflux, we drew distillation, we looked at the differences. Oh, I've got an equation there that's not balanced. Don't like that. Just going to add water in there like that. There we go. I don't like that. And we talked about their boiling point and where DDs, of course, this one's suddenly going to drop. Instead of being 78 for the alcohol, we now drop to about 25, maybe even less for ethanol. It boils at about, that's the one that nearly killed me. That one is, boiling point around room temperature. And we talked about all this. And then at the very end, we talked about kind of the questions that you might be seeing. So why do we want a reflux? What's the function? Why the distillation in terms of selecting for the aldehyde, etc., etc. So what I'm now going to do is I'm just going to finish that off. Just going to finish that bit off. So one of the things that is covered here. So it then says in your specification, primary alcohols to produce aldehydes, give a positive test, right? We need to do the tests. Primary alcohols to produce carboxylic acids, give the test. So the one's under distillation, one's under reflux. We now need to confirm the people we've made. So can you put tests for ... Okay. So the first thing is how can we test for an alcohol? Now you learn to test for an alcohol at GCSE. So test for alcohol, and we've already got one. which is you can test with number one, with acidified, shouldn't do it, I don't like it, with potassium dichromate, and blank. Pause the video, fill in the missing blank. They love this one. Everyone tends to learn the horrible long name and forgets the extra bit. So pause the video, fill it out. And the answer, of course, is dilute H2SO4, dilute sulfuric acid. Now that test will flag that one there. With a primary, it'll turn green. For a secondary, it'll turn green. But a tertiary, it does absolutely nothing. No reaction. That's, by the way, that's actually what you write. Lots of students picked up from the internet a couple of years ago, no observation. That means you did it with your eyes closed. So no reaction is the right response. Now that means there's a problem. There's a problem because that's a negative test. That's a negative test for a tertiary alcohol. That's not ideal. We need another test, another proof. So if we got a negative test for that one, how do we prove it's definitely an alcohol? So test number 2 is to add sodium metal. Sodium metal. And that's it. Just add sodium metal and we will see fizzing. If you want to write effervescence, you can. Yeah. Effervescence. I don't know, something like that. Effervescence. I don't know. Something like that. Can you use another acid because of this all supply H+? Oh, Kayun! What an amazing question. No, you can't. The reason being, okay, wow, reason for acid choice. Okay, so acid choice. Right, so just to explain, acid choice, idiot. There you go, acid choice. So potassium dichromate, K2Cr2O7, is quite a strong oxidizing agent. This is an oxy agent. And if you notice, if I look at all 3 acids, in fact, all 4 acids, so we've got hydrochloric, nitric, sulfuric, and ethanoic. So the first thing I want to get rid of is we're going to say no. We're going to say no war. That's just ridiculous. Come on. My tablet is already causing me trouble. I don't know why it does this. I have no idea. So ethanoic, definitely no. The reason being is because it's weak. Weak acid, not enough H+. I think everyone would kind of agree with that. The next thing is that you can't use hydrochloric. The reason being is that the hydrochloric acid is only monoprotic. This is only going to give me 1 H+ per molecule. This is said to be monoprotic. Now, what that means is you're only going to get 1, which means if you look at the equation, for me to go from the dichromate ion to chromium 3+, which is green, Moe, let's do guys, really good chance to do a bit of redox revision. Guys, pause the video and balance my half equation, please. Okay, metal, 2 and 2. No, 2 and 2, 2 and 1. Next, water for oxygens, 7 H2Os, because each one gives me 1 water. Next one, acid for H+. I've got 14. Whoa, that's a lot of acid, folks. That's a lot of H+. Right, now, electrons for charge on this side. we've got plus 14 and minus 2, that's plus 12. On this side, we've got plus 6 and 0, so plus 6. Bring somebody down, plus 6 electrons, and I'm done. There we go. Electrons. So I need lots of H pluses. So monoprotic, in order for me to get hydrochloric to give me enough, I'm going to have to make it quite concentrated. Oh, Dinesh, hi Dinesh, good to see you, dude. So we're going to have to make it concentrated. Now there's a problem with that because you're also going to have this guy. And here's the problem. It's in a -1 state and it can be oxidized. This can be oxidized to chlorine gas. And it will readily be done using potassium dichromate. So you can't use hydrochloric acid. Can't use. So at this point, I kind of need to add up the notes up here. So this one, I'm just going to put my arrow saying not sufficient. I'm going to make my pen really thin. Not as thin as I can get it. Not efficient, not sufficient H plus when dilute. Oxidized to chlorine gas to Cl2 when concentrated. Can't use it. Nightmare. Next. Right now you've got to decide between these two. Now these two, of course, you've got another monoprotic nitric acid. So nitric acid is monoprotic. H plus NO3 minus. So again, monoprotic. What that means is it's going to be insufficient on dilute. Therefore, we're going to have to make it concentrated. And what could happen is Julian's here. Good to see you, Julian. The nitric acid could start oxidizing the alcohol. The reason being is nitric acid is in quite a high oxidation state. Right, so the nitric acid is in a +5. And it can go to NO2, which is a +4. Right, guys? Can you away, please? Can you balance my half equation, please? Off you go. Pause the video. Right? So metal is nitrogen in this case, because remember that the water gives us oxygen. H2O gives us oxygen. Acid gives us hydrogen. And electrons give us charge. The M is anyone else. I tend to call it metal because it goes with them away. But in this case, it's nitrogen. One nitrogen, one nitrogen. This is good. Next, oxygens. I need an extra water over here. Right, hydrogens. 2 and 1. Going to have to, not going to double that. I'm going to add a H plus. Right, and balance for charge. There we go. 1 electron. There we go. If you're wondering how I did the electrons, it's +1 here, 0 here, overall +1. Over here, no charge, 0. Bring somebody down, add the electrons to there. So this can act as an oxidizing agent. And what you're going to produce is toxic nitrogen dioxide. And that is not a good plan. So this one is the notes for this are going to be, it's monoprotic. I'm not getting rid of that. We're going to say insufficient H plus when dilute, same result. Oxidizes alcohol to produce toxic NO2. Not a great choice. So we now get to sulfuric. Sulfuric is the right choice because it's diprotic. It's diprotic, so we can use it dilute, which means it won't oxidize the alcohol and produce SO2. Nice. How cool is that? Great question, Kayan. I bet you didn't expect that answer, did you? Holy mackerel. Amazing question. Superb. Right. So just to give you the equation. Oh, I think I may have done this with you guys already. Guys, ethanol plus sodium metal. Complete the equation really hard. Pause the video. If you don't know, just stay around and watch. So complete the video, complete the equation. So we get CH3, CH2, ONA, and hydrogen. You get a half. There we go. And that comes out as a gas. If you want to see what that looks like in displayed, there's the ethanol. Here's the sodium. The sodium, of course, gives away electrons to the hydrogen to form a positive ion. It becomes ionic, dissolving very well into the solution, by the way, into the alcohol, by the way. And there we go. And I then form hydrogen gas. Half. There we go. Nice to see it. So these are the tests for alcohols. I'm wondering if there's any others. Another test for an alcohol. I'm tempted to say, I don't even want to say it actually. Anyway, so now that we've tested for our alcohols, those are the main two tests. We now need to test for ... aldehyde. There we go. Aldehydes. CHO. Gotta love a good CHO. So we've got C double bond O H. So this is what we're testing for, folks. That group. Emma, potassium permanganate. Oh. Are you saying could you oxidize it? Emma, I love the lack of effort in your question. I assume your question is, can I use potassium permanganate as an oxidizing agent? Is this correct? She's then just put, yeah. Is that correct? I'm quite curious to see what the delay is. Okay, yeah, okay. Okay, no, you can't, Emma. Great question. Now, the reason why, oh man, you guys have asked like crazy questions, but they're all such great questions. So you can't use, right, I need a bit more space than that. Right, K2Cr2O7 versus KMNO4. Let's draw them both out. It's always nice to do these. I don't often get to draw these out, so I kind of take the opportunity any chance I get, really. So it's a great question, Emma. It's a great question. Here's potassium dichromate. Here's potassium permanganate. Oh, it's not an M, it's an MN. There you go. There's the permanganate ion. Not that you need the lone pairs. There you go. If you're wondering where the potassium's gone, it's ionic at the top there. There we go. Right. So, by the way, me drawing them out is not really required here, but it's nice for me to do this for those dot and cross diagrams that EdXL love to ask. Now, the reason why you can't use this, this is more powerful. This is a stronger oxidizing agent. Stronger oxidizing agent. I'll put, there you go. Then that one, weaker oxidizing agent. The reason why is because the chromium is in a +6 oxidation state. Oxy state. And the manganese is in a +7. That's crazy. It's crazy oxy state. Madness. So it's actually going to want electrons even more readily than the potassium dichromate. So if you were to take an alcohol, if you were to take ethanol and add potassium permanganate as an oxidizing agent, I don't know why I decided to do that, as an oxidizing agent, and this is KMNO4, it does something even more bonkers. It is so powerful, it rips it apart entirely to form CO2 and water. Balance the equation. 2 carbons, 2 carbons. Hydrogens, 6. Hydrogens, 6. Oxygens, 7 on that side, 2 on this side. So 6 here. I think that then adds up. There you go. There we go. So it actually is such a crazy powerful oxidizer. It actually sets fire to it. It's actually a boss reaction. If you ever want to watch this, there's a demo of it, which I do, and I would have happily done for you guys. You do need to add acid, of course. This is with dilute sulfuric, because you have to because you realize that the oxidizing agent is going from MnO4 minus to Mn2 plus. Right, guys, redox, away me, please. Balance my half equation. Off you go. Balance my half equation. Pause the video. Have a go. I'm having fun today. This is fun. I haven't managed to do any of what I'm trying to do, but there you go. Metal, 1 and 1. Oxygens, 4, add water. Metal done, add water. Need 4 waters for 4 oxygens. Next, acid for protons. 8 hydrogens, 8 hydrogens. Electrons for charge. On this side, plus 8, minus 1, plus 7. On this side, plus 2 and 0. It's on a plus 2. Add 5 electrons to bring it down. Whoop, whoop. There we go. Smashed it. There we go. I like it. Next. Do you know what? Since we're doing it, holy moly. All right. Since we're doing it, it's not my fault. Blame Emma. Ha. Hey, Jassim, good to see you. It's nice to see you attending an AS webinar. That's great. Good revision for you. So let's just do the other one as well. Can everyone do this one, please? Ethanol to carbon dioxide. Moe me, please, folks. Moe me. Right, there we go. So pause it. Have a go. Metal, carbon. So the carbon's acting as an electron here. Yeah. So carbon, 2 carbons, 2 carbons. Oxygens with water. 4 oxygens, 1. 3 of those. Next, acid. Hydrogens, whoa, it's a lot. It's a lot. 6 plus 6, 12? Seems like an awful lot. 12. It doesn't actually. Organics requires loads of them. Next is hydrogen, sorry. Electrons, plus 12. That's easy. Plus 12 electrons. Nice. Nice. Right? We're doing well here, folks. Next. Right, now that we've got that, we can put them together. That would be cool, right? Have I done it all? Have I balanced that correctly? Let's just check. 2 carbons, 2 carbons. Oxygens, 4. Oxygens, 4. No, that's correct. H pluses, 6. 6, so 12. Definitely 12. There we go. Okay, no, it adds up. Right, let's now put them together, folks. Now remember, in order to put equations together, we're going to create the overall here, folks. Yeah, the overall equation. In order to put them together, you need the electrons to cancel. Now that's a bit of a nightmare. 5 and 12, yuck. This is going to be massive, folks. I don't really like it. I don't really have any choice, though. Times by 12, times by 5? Oh, man, that sucks. All right. Times 12 times 5. You'll notice, by the way, I'm just multiplying them by the electron numbers. It'll mean they'll disappear. They're going to be massive numbers here, folks. I'm going to switch to red. So that now becomes 60. Yeah. 8 times 12. I'm doing this on the calculator. 96. Oh, my goodness. 96. 12 of these guys. 12 of those guys. 12 times 4, 48. Yeah, 48 of those guys. Right, let's multiply this by 5. 15. Yeah. 15, 5, 10, 60, they're about to vanish. And electrons, 60, nice. Okay, put them together. Electrons vanish. All of these vanish, minus 60 from this side. Minus 60, 36. Next, waters. All of them are going to vanish. 15 of those are going to vanish. 48 minus 15, 33. Holy moly. 33. Anything else? No. Okay, final overall equation is going to be 36 H pluses plus 5 CH3s, CH2OHs plus 12 MnO4 minuses goes to 12 Mn2 pluses plus 10 carbon dioxides plus 33 waters. What? And that's why they don't want you to do that equation. What a nightmare. That's a pain, isn't it? It's a mess. Oh well, is that what everyone else got? I'd really like to see if you guys could check that for me. Can I simplify this? I really want to simplify it. I don't think I can. What a nightmare. Anyway. Oh. It should have appeared at the same one as that. No, because we're putting the Mn in properly. That's why. Oh, we need a lot of acid. Lots and lots of acid. Anyway, next. I really want somebody just to confirm that they got the same equation as me. That'd be really handy. Anyway, going back to this. Okay, so how do we test for an aldehyde? I'm back onto that. I've lost where. Oh, there we go. There we go. Test for an aldehyde. Back to there. Okay, so the test for an aldehyde is going to be 2 tests. You can do 2. So the first one, number 1, is going to be what's called Fehling's solution. Fehling's. By the way, in biology, it's called Benedict's, but it's in a different condition. This one's in acidic condition, whereas Benedict's is in an alkali condition, just so you know. And Fehling's solution on contact with an aldehyde will go from the observation. So with an aldehyde, it'll go from blue solution to a brick red precipitate. And yes, you have to say that, PPT. A brick red precipitate. With a ketone, no reaction. So this test is actually used to distinguish between the 2 families. There is another option, which is called Tollens reagent. Tollens reagent. And with the aldehyde, we will form a silver mirror precipitate. We would usually be doing this in class, and it's one of my favorite practicals. With a ketone, no reaction. There we go. Cool. So those are, can you say orange red instead of brick red? Yes, definitely. They'll allow that. It's absolutely fine, Julian. For sure. Orange red would be fine. Cool. Silver mirror precipitate, or a grey precipitate sometimes, depending on whether or not it forms a silver mirror or not. Why would you use one over the other? Good question. Depending on which ones you've got in the cupboard. Yeah, it's a really good, the answer is you can use either, Nikita. And it just depends which one you're more comfortable with. By the way, both tests, just so you know, both tests require warming, require heat. They don't work unless you warm them. Yeah, they both require heat. So if they asked you for a method, you'd say add failing solution and warm using a water bath. Does that make sense? So yeah, require heat. It's because they're organic reactions, guys, and we've got to break bonds. Therefore, they have high activation energies. I think most people are all okay with that. Next. Right. So now that we've figured out we can test for the aldehyde and technically a ketone, what we can now do is test for the carboxylic acid. Test 4. Gonna make my pen a bit thicker. Test 4. ... You might want to put these on a single sheet, folks. It'd be easier. A carboxylic acid. So this is a coo. It's a pigeon. Everyone knows the pigeon. Coo, coo, coo. I'll stop. I'm sorry. It's been a long week. There we go. So there's the structure we're testing for. Yeah. How do you test for this? The test is sodium hydrogen carbonate. And what you're going to see is fizzing. Observation. There you go. Observation is fizzing. You can then test it for carbon dioxide by bubbling it through lime water if you wish. Do you want the equation? You want the equation, don't you? Ugh. Okay. So let's go for ethanoic acid plus sodium hydrogen carbonate. Off you go, folks. Pause the video. Have a go. No. No? Dinesh, you can't just put no. What does that mean? Is it no to having a go at it? Anyway, so all that's going to happen now, folks, is going to form a salt and water and CO2. It's nice and easy. The salt is sodium ethanoate plus water plus CO2. There we go. Not complicated. Julian, question. I know, right, Julian? I haven't got a clue either. There we go. Nice and easy. So we just see fizzy from the gas. There we go. Nice, easy test for carboxylic acids there. Nice and straightforward. Am I still missing Ben? Did Ben still not arrive? That's very upsetting. Neither did Ria. No Ria, no Ben. Not impressed. Forced to save. There we go. That makes me sad. Does magnesium ribbon work as well? Ooh, no, Julian, it doesn't. It would just be flat out too slow. I mean, I guess it could work, but you could argue that that would work for the oh no, that definitely wouldn't work for the alcohol. You could potentially use magnesium if you wanted. I wouldn't recommend it. It's definitely something I wouldn't say I'd do normally in an exam. I don't think I've ever covered it. I can give you the equation if you like. All right, magnesium. Is that really wanted? Plus ethanoic acid. It will fizz. It's going to give off hydrogen gas, metal and acid, MASH, metal acid, salt and hydrogen. It's a bit more complicated because you're going to form a magnesium salt, which is going to have 2 ethanoates on it. That's much more complicated. If you want to use that one, go right ahead. But it's tricky. There you go. Magnesium ethanoate. Magnesium ethanoate. There we go. And fizzy hydrogen gas. You could even confirm hydrogen gas with the squeaky pop test in practical 7. Oh, yeah. In practical book says magnesium ribbon. Yeah, cool. Like it. Sure. What's the title of that practical, please, Julian? Is that titled chemical test or is that rates of reaction? Quite like to know. Anyway, nice shout there. I like it. Okay, so we have now, it's nice to go back to here. So, number 1, primary aldehydes, failing products of distill, yet done it. Primary alcohols produce carbon reflux, done it. Oh, look, test. Benedict's or failing solution. That's rubbish. No, ignore the Benedict's. Oxidation of propanol to produce propanol and propanoic acid. Oh, okay. And then test for the propanoic acid magnesium. Huh, interesting. Well, do you know what? Problems with that, just to say. Actually. Yeah, no, yeah, I'm happy with that. Sure. Benedict's. Edexcel. No. Sodium hydrogen carbonate. There you go. No, it's not sodium carbonate. That's not true. Oh, I hate that. Edexcel, stupid chemists. So, guys, that's not true. If you put, let's do. I'm not sure. Alexa, stop. Stupid Alexa. So we've got sodium carbonate versus sodium hydrogen carbonate. That is not a good test. No. No. The reason why that's not a good test is if you mix that with ethanoic acid, what's going to happen is the first reaction you're going to get is you're going to form the hydrogen carbonate. You're going to form the salt, which has no observation, and you're going to form NaHCO3, and you're going to get no fizzing, no fizzy. What that means is that's not a good test. You'd have to add more acid. You'd have to go again. So you're now going to add another acid to it to react with the hydrogen carbonate. I'm then going to combine the equations, by the way, to form, there you go. I can combine the two of them to form CO2 and water, and then I can add these two equations together. So I can go cross out, and I'm done. So it now becomes 2 of those, 1 of those, 2 of those, and the H2O and CO2. So I'm just, by the way, I shouldn't do that. It's really bad for me to, I should just write out the equation again. I've got 2 of these. So the overall equation is 2. You've got to add excess oic acid to make that question viable. Don't agree with it. Because you'd add it. You'd add, whenever you're doing, you guys remember from GCSE that you add the tiniest amounts of stuff. And if you add a tiny amount of that, you're not going to see any fizzing because you're just going to form the hydrogen carbonate, which is soluble. It's a nightmare. Bad chemistry there at Excel. Next. Ketones, equations, yada, yada, yada. Give the test for it, done. Okay, next one, heating under reflux. Everyone here is okay with this. Extracting a solvent using a separating funnel. Right, I wanted to show you guys a separating funnel. So I got a couple of pictures off the internet, off the Tinterweb. Get on that internet. So, and this is what a separating funnel looks like. By the way, there are others. There are ones that aren't pear-shaped. There are ones that are vertical as well. Just to let you know, this question does appear regularly in Unit 3. In Paper 3, they commonly talk about separating funnels. And what they'll commonly do is they'll give you different liquids. They'll give you like liquid A, B, and C, and then they'll go with water, with H2O. And what they will do is they will give you the densities of the liquids. So the density of A is 0.78 grams per centimeter cubed, by the way, if anyone is wondering what the units are. Grams per second, because it's mass per volume. Yeah. A is 0.78, B is 1.25, and C is 0.52. And what they will do is they will say to you which one of the two would sink, would be at the bottom of the separating funnel. And this picture here with the two liquids, the one on the bottom is always the more dense. Now, at this point, there are people, and this one is the less dense. This one, people are now sitting there going, well, hang on a minute. You haven't told us the density of water. The answer is, guys, you have to know it. And the density of water is 1 gram per centimeter cubed. You guys have to just know that fact. Mia! Oh, my goodness. I forgot to register. Mia! Ah, there you go. I'm putting you in. No, I won't mark you as late. I'm going to be nice. I'm too nice to you. I like you, Ria. There you go. I've been here for like half an hour. Lol. Well, you're still late in that case. I'm being nice to you. Anyway, so the less dense will always be on top. So the only one that would sink would be B. The only one that would be on the bottom would be B. The other two would be floating. If you put A, C, and water in, C would be at the top, A would be in the middle, water would be at the bottom. Yeah. Anyway, so these are very common questions that they tend to do. So extracting with a solvent using a separating funnel. Right. I don't really want to be. I can do extraction with a solvent. I'm going to do a lesson on steam distillation. I need you to remind me. When I do steam distillation, can everyone remind me just to also do extraction using solvent extraction? Is that okay? Solvent extraction. Otherwise I'm not going to get through any of what I wanted. Distillation we've done. Drying agent. Right, guys, whenever you do any organic prep, you usually tend to have water around as a contamination. So to dry an oil, I know this sounds really weird, but if you want to dry something, a drying agent is calcium chloride, top answer, or calcium sulfate. Whichever one you want to use. However, I prefer calcium chloride. It's the better one. It's my drying agent of choice, don't you know? But there were two for you. Boiling temperature determination. This is using your WIMPs, of course, folks. Yeah. Deciding whether or not they're HBs, DDs, or LDFs, London Dispersion Forces / VDWs, Van der Waals Forces. And then you can then compare them. This isn't a determination. Yeah. This isn't a determination, more like a comparison. Okay. Now I've only got 10 minutes left of my lesson. What a nightmare that is. Other reactions of alcohols. Right. So I'm going to do other alcohol reactions. Okay. So what we've so far covered is we can oxidize an ol. That is the first thing that we've done. Number one, oxidation. Next, what we can also do is we can do what's called halogenation. Halogenation. Now, this is actually a type of substitution in this regard. It is a substitution in alcohols. What we can do is we can swap the alcohol group. We can swap the alcohol. No, Mr. Duncan. No. We can swap the alcohol group for a halogen. So how do we do this? Right. There's two methods that you guys need to know. Number one is you're going to use PCl5. This is a powerful halogenating agent. It's a bit of a crazy one, to be fair. It can also, it's another test. Can also test for ols, for alcohols. Because primary, secondary, tertiary all react with it. And what will happen is that I will get what's called POCL. I'm going to do one example of ethanol. So if I take ethanol and I add I add PCl5. Powerful agent. First thing that's going to happen is I'm going to swap the OH group for a Cl. First thing that's going to happen. Yeah? But the question is, what else do I get? And what I also get is cool. Cool. It's actually cool. Yeah, because there are 3 cools. And HCl. Sorry, I'll stop. So I'm going to get rid of that magnesium equation. There we go. So we make Pockle. And people say, how can this be used as a test? Because the hydrochloric acid is given off as misty white fumes. Oh, I got water on my tablet. Misty white fumes of HCl. Powerful agent. It even balances, I think, if you notice. It's a great equation, that. I always like Pockle. Pockle. It's how I remember it. It's how I remember that POCl3. Next, right, what else can we do? We could also react it with 50% concentrated sulfuric acid and KBr. Now, the reason why, do you guys remember redox? We've been doing some redox today. It's been fun. Do you remember redox? So the solid ionic sodium or potassium halides with concentrated sulfuric acid. Do you remember all that jazz? Holy moly. That's a long time ago now. But what's going to happen is this reaction is going to produce HBr in situ. Produced in the beaker. HBr is an acid and it's a gas. We don't usually have it. Produced in situ. Now, what that means, in situ, is that how you spell situ? Or is it just situ? I think it's just situ. I don't know. I say it, don't spell it. Situ. Is it with a U? I don't know. Anyway, produced in situ. Well, that means it's made in the beaker. Yeah, you also get you're also going to get SO2. You're also going to get bromines. Going to be a bit of a nightmare. But the 50% limits all those other side reactions. We still get, in fact, no, hang on a minute. I tell a lie. The 50% stops it. We go for a straight swap reaction. We produce K2SO4 and it stops because it's 50%. If it was 100% conc, you get all the other redox products. But in this case, it's more dilute, so you only get these. Right now, the HBr can now swap with the alcohol. So that now reacts with it with HBr to produce a bromo. Oh, a bromo and no, what am I doing? What am I doing? And water. There we go. So that's the other one. The last one, and this brings us to the end of the lesson. 3 minutes to spare. Last one is concentrated phosphoric acid. Some of you might remember this if you learned your GCSE well. Yeah. Oh, I think everyone's gone. That's hilarious. Concentrated phosphoric acid. You're going to go through elimination. This is going to go through elimination, folks. Guess what you make in elimination? You're going to make an alkene. So we take an alcohol, and it's going to then add your phosphoric acid, and you're going to form ethene. Right, guys. 9 people still watching. That's good. Right. Let's see what I've covered. Tertiaries. Combustion. Haven't done it. Halogenation. Pockle. Like it. KBr. I've missed one. Red phosphorus and iodine. Blimey. Iodos. Right. Can. I'm going to be a bit late for my year 13s. Can. So this is red phosphorus. red phosphorus and iodine. So first reaction, P is actually P4 plus I2. Going to react those separately and you form PI3, phosphorus triiodide. Balance the equation. 4 phosphoruses, 12, 6. There we go. Phosphorus triiodide in situ. And then, of course, you're going to form, and then that's going to swap out for the iodine. The question is PI3, and we're going to form I think it's probably going to be that. And HI probably. Oh, no. No, you're not. Oh, you're not. There's only 3 of them. It's not as strong. It's going to swap out. You're going to form... Oh. You're going to form phosphorus hydroxide. Or phosphoric. Oh, no. Guys, you're going to form phosphoric acid. Ha. That's clever. It's not strong enough to... It's going to form phosphoric acid, isn't it? H3PO4. Sorry. Made a mistake there. H3PO. Let's balance it. The balancing will tell me. Oh, it's going to be a nightmare, isn't it? So, iodines 3 and 3. Alcohols, therefore, need 3. Phosphoruses, I've only got 1. Oxygens, I haven't got enough. There's not enough of them. Because H3PO4. Oh, no. Oh, I don't like that. Oh, would an alkene and water be the only products from the elimination reaction? Yes, the phosphoric acid's a catalyst, Ria. Great question. Thank you. Ooh. Am I going to need water somewhere here? No, it all adds up except for that. Is it phosphorus acid, not phosphoric? No. Oh, I may have just been beaten. I haven't done it in a while. That's hilarious. Google. This is where Alexa might have been handy. Let's have a look. Ethanol and PI3. Go. Images. Oh, that's not it. Phosphorus triiodide. I bet I have to write phosphorus triiodide. Ethanol and phosphorus triiodide. I got beaten. Going to be late for my year 13s. Damn. Images. What am I going to get? Come on. Oh. No. Not helpful. Oh. Guys, PCl3 is there. It's phosphorus acid, not phosphoric. I knew it was. Darn it. Yeah, then it adds up. And we're done. Hey guys, what is situ again? It means it's being made in the beaker. So I haven't had to add it. It's like the first reaction produces something else in the beaker that I haven't needed to add. It's being made in situ. Anyway, guys, that brings me to the end of my lesson. I'm going to be a little bit late for my year 13 one. Oops. Let's go back to this. I've got to turn my camera back on, enable, and then go start camera, see if that now works, and then go that one. Hey guys, thank you so much for coming. I know it's been a long lesson, that one. It's been a full hour, about an hour and 3 minutes. I'm going to love you and leave you guys. I hope you have a nice rest of your day, folks. Take care of yourselves. See you soon.